Okay. Shall we wait a few minutes or shall we start? What do you think? Maybe just a couple of minutes that people
can, yeah, maybe we can wait a couple of minutes more.
I agree.
People arrive. But so it's even more difficult for you in some sense, Laura. Okay, can we keep talking about this, or just because we are live on YouTube?
I mean,
I think we have like maybe 2 views on YouTube, and one is.
I think it's like
the other one.
The other one is Alessandro.
Yeah, I think YouTube is not our, let's say, best channels of communication, because there we had an average of 5 people online, and we are 5 organizers. So I guess we are.
No, I think we had Karsten students on YouTube, because on the first day I was afraid that we might hit the 100 connections on Zoom, which is the limit of this account. And so I recommended them to go to YouTube. So we had like 9 or 10 connections on Monday. Yeah.
But we were too optimistic. We never reached 100.
Yeah. No, not yet. Maybe today. Let's see.
True.
Anyway, so I guess it's really tough to manage a research group from home. Or are they muted again?
No. Everyone can unmute himself.
Okay.
I mean, I'm coming to work, so it's.
Okay, you are.
Okay. Yes.
Okay.
And can you do the measurements, or are they stopped?
Not really. I mean, they were stopped when we were in the red zone. Now, in principle, you could, but the issue is that usually we use like students as subjects, and there are no students at the moment at the university, so it's
complicated. Yeah,
it's a bit complicated. Yes.
And because also I saw from Twitter that there are a lot of PhD students in trouble for this, because most of their projects maybe just started last year and they had to do the measurements and they can't. So they were actually starting to review paper, but it's not the same. I mean, it's not like learning to take measurements.
In Germany, the German Research Foundation really unbureaucratically prolonged projects. So it was just, let's say, you had to make 2 crosses and you had to sign, and then I could prolong a running project by something like 3 months very easily. So I have never seen such an unbureaucratic procedure in Germany, because normally all procedures are rather bureaucratic.
Yeah.
It was really easy, so that I would say the PhD students of my running DFG projects were really finally winners of that whole procedure, because the analysis of data was possible like before, and they got longer time. Only the measurement of new subjects, that was more sophisticated, but we also found our ways, and our decanate allowed us to do measurements under certain conditions, Corona conditions, and finally it was okay, I would say. I don't know, did you have something from Italian funding agencies for such Corona measures, or was it not existing?
I mean, not really. The only measure that was taken is to like prolong, in Italy, like PhD lasts 3 years, so no matter whether like you have more to do or not. So basically all those students that were in the 3rd year, they could have 6 months prolongation if they asked for, due to Corona, and that was good. But that was limited to those who were supposed to finish their PhD training. Yes.
And new projects, I'm still waiting for a project application that we submitted 1.5 years ago, I think. So new projects are waiting and running projects are prolonged. This is how they fund it, I think. Let's say everyone who has submitted a grant proposal is the loser, and everyone who has a running one, which comes to the end, is the winner.
So they did not invent new money, basically.
No, that's, I mean, they currently do everywhere in Europe. Yeah, I don't know who will pay this big debt that we are accumulating. Billions over billions. And let's see, the bill will come, yeah, to all of us. I think we will all have users or something.
Okay, I think we can maybe start now. What if you agree? Okay, so welcome everybody to the last day of this workshop. Today, the main topic of the day will be connectivity. And in particular, we will start, I'm really honored about this, with a talk from Guido Nolte. He is currently professor at the Department of Neurophysiology and Pathophysiology of the University Medical Center of Hamburg, where he leads the group focused on magnetoencephalography. And we asked him to do an introduction to the most widely connectivity measures, since I guess everyone here knows him for his contribution to coherence-based connectivity metrics. So please, Guido, go ahead, the stage is yours.
Okay, so thank you. Let's get started. So it has 3 parts. The first one is completely basic. So if you're familiar with it, I doubt that you will learn anything new. I just want to explain what phase locking value is and what coherence is to people who have never heard about it. And the second part, so this is here on this is on nonlinear data analysis. So that part is not entirely new. So that's something between tutorial and talk to present something new. So in general, I would say, so please interrupt me anytime. I actually appreciate it. Sometimes I find it weird to talk to a computer and then I appreciate if people interrupt me. Okay, then I start about phase locking. So anybody you can hear me? Everything is fine there?
Yeah, it's perfectly fine. Thank you.
Okay, so this is the typical situation we have. We have data. So on the left we see typical measurement of EEG data in some frontal channel. You see some oscillations here or fluctuations there and something which is slower. And in occipital channels, the typical observation you have looks like this. You have a more clear oscillation, in fact, at 10 Hertz in this case. That's called the alpha rhythm, but there are also slow parts in it. And what people in EEG, when studying rhythms, they are mostly interested in studying to understand implications of this rhythmic part here shown at 10 Hertz. So how do we study this? First of all, we could have a qualitative look at, for example, at 2 channels, and this would be here. This would be some half a second part, another half a second part, and so on. And then what we see in such a picture, first of all, there are 2 channels, and we see, yeah, there might be some oscillations, but in general, this looks far too wiggly, too many fluctuation to really understand anything from this by just looking at it. But since we are interested in the oscillations only, at least at this part, we can do something about it. So in this case, the first thing we can do is we filter data. So in a band, say near 10 Hertz, say between 8 and 12 Hertz, and we get these pictures now. This, of course, now we see clear oscillations, but this is also be part of the fact that we have filtered the data, so that by itself doesn't mean anything. But these oscillations, they are real, and in the power spectrum we can clearly see that they are much stronger in amplitude than at neighboring frequencies. And then we can first look at it qualitatively and see what we can tell about it, whether there's anything we notice from these oscillations. And what we see here, first of all, in different segments, half a second segments, they slightly vary in amplitude. Also within one segment, amplitude is not entirely constant. But there's one thing we can observe through all segments, and this is that here we have a red and a blue channel, or red and blue signal, and the red one is always here a little bit to the right to the blue, here it is a little bit right to the blue, and so on. Pretty much always. There seems to be some systematic relations between these two channels. Now we can observe this qualitatively, but whenever you do coupling measures, the point is to put this qualitative observation into some numbers and quantify how strong the relation between the two channels is. And now to do this, we must first of all simplify data a little bit. We started here, for example, we have seen here some raw data. Such raw data is still enormously complicated, even in one channel and in one segment. So we simplified it. What I did before was just filtering. So when we filter this, it looks like this red signal. This looks like a clear oscillation, but it's not as simple as it really looks like. For example, the amplitude here on the right is a little bit higher than on the left. The time difference between these two peaks on the right is a little bit different from the time difference here on the left. So this would be still too complicated to put easily into numbers. So what we do is, rather than filtering, we make a model. So in this case here, the black curve, that's not a filtered signal, it's a model. So we fit a model consisting of a sine wave with which only specified by two numbers. One is the amplitude and one is the frequency. Frequency actually means the time difference between these two peaks. And these are the only numbers we are interested in the following, at least for one segment and for one channel. Here, typically in courses, then I ask how you actually fit such a model, and the answer to this is that this is what a Fourier transformation is doing. So this is equivalent. A Fourier transformation for each frequency fits such a model. So now we have this black curve, and we can characterize this black curve just by two numbers. And with these two numbers, it's much easier to work than with a full function there. So this is again, illustrates it again. So we have oscillation that's determined by two quantities. One is the amplitude A, and one is the phase, or the delay, the position of the peak. That's also called the phase relative to the starting point of this segment. And this these two numbers we will analyze in the following. Actually, there's a complex. We can write this as two numbers and write as a sine function or cosine function, but a complex representation of this just one complex number, and this complex number is constructed from two real numbers. One is the amplitude A, and the second is the phase phi. And it's rather than treating A and phi separately in many formulas, it's easier to actually use this complex formulation with a variable z. But here we are even interested in less than these two numbers, but we are only interested in one. What the original idea is we want to see whether the phase difference between two channels, whether there's anything systematic or they are random. They're random. So the only thing we are now interested in is the phase difference between two signals. That's some delta phi. And this, when we only analyze delta phi's, we will come up with a measure of phase locking. In coherence, this is a little bit different. I want to start with phase locking, not because I think it's better than coherence, which from the construction is a little bit more complicated, I would say, but because it's easier to explain. I prefer coherence over phase locking, but that's also some details. So in practice, phase locking or coherence, if you just look at the numbers themselves, that makes almost no difference. Okay, now, but the question was not how is it in one segment, but in across all segments. So we want to see whether a phase difference is systematic, is stable across segments, the phase difference between two channels, or not. So this is when we have many segments, or here written as trials, and we always write the phase difference. This is as phase difference here normalized between, divided by 2 pi, so then it's normalized between 0 and 1. So we look at the phase difference across all segments, and then we must decide whether the phase difference is random or whether it's systematic. So apparently what you see here, it is something in between. And we want to quantify how stable it is. Now, how do you quantify whether some variable varies a lot or not? The typical quantity here is you calculate a standard deviation, a mean and a standard deviation. So this is how you would, this would approximately come out. So the mean is of the phase difference approximately here, and these then denotes the standard deviation. Now this picture that looks like a meaningful way to do this here, but in general, this is not a good idea to do it like that. And then, so I want to show you why this can also be very bad. Actually, in this case, it's also not really good, but in general, it can be really bad to do it like this. Therefore, and to do this, I'll show you a different case. So here's a case. This is also a measurement. So phase difference between two channels. And you see many phase difference are here close to 0, slightly positive, and other phase difference are mostly close to 1. And when you calculate a mean here and a standard deviation, mean would be around 0, and the standard deviation would be huge. This is not really what it means. In this case, the phase difference is always the same value. And the reason is that a value, this is a value close to 1, or the line 1 is identical to the line 0. So it's just periodic. And this would be an example where we like two neighboring channels where the phase difference is almost 0, but sometimes it can be a little bit negative and sometimes it can be a little bit positive. So it's very, very stable. If you use mean and standard deviation, you would get it totally wrong. And to address this, we need other kind of statistics, and this is called circular statistics. So what we do here then is we don't look directly at the number phase difference, but the phase difference is in fact mapped to a point on a circle. So the number delta phi is then represented in this case by this point on a circle. And you would see if it's close to 0, so it can be slightly above 0 or almost a full circle, then it would be slightly close to pi. The value is very different, but the point on the circle, they would be almost identical. And these points on this, then we analyze the points on the circle. So I show you some example how this would look like. So this would be approximately this case. So we see, so in this case, faces close to a full circle, not quite a full circle, but close to a full circle. Then these, what is red dot here on the left, these are the blue dots here. So the blue dots are concentrated in this part of the circle. And if you, in the other case would be like that. So we have points close to 1 if we normalize it by 2 pi or close to 0. And these red dots here are the blue dots here, and they are always close to the right side. So, and then we analyze these points on the circle, and in fact, we just average the points on the circle. So in this case, what you see, the average of these vectors of the blue points as vectors would come up with some specific vector, and that in the mainly points to where most of these points on the circles are, and this is a relatively long vector. And the length of this vector, that would be called phase locking. So in this case, you would see it's very long, so it's very stable. Phase locking is very high, and the other case also it's very long, almost close to 1. So also in this case, phase locking would be very high, which represents in the fact that phase difference is quite stable. Now, of course, it's not always the case. It can also be unstable, and then we can look at other examples. For example, this you see here, that was the example before, very stable. Here, very stable, but you can also have, this would be the case when the phase difference is actually really random. Then we take an average of all these blue points or blue vectors, and the average of this is in fact so small it always looks like a point, but it's really just a very tiny vector. So this is what phase locking means, and that's really it. That's what phase locking means. I want to now come to coherence, at least qualitatively. This was again another one example of phase locking. Phase locking here is relatively high. Phases are concentrated to the angle of 270 degrees, and then we get a relatively high phase locking by simply averaging the points on the circle. In coherence, the only difference is that in coherence, you don't directly weight the points on the circle, average the points on the circle. Each point on the circle gets a weight according to the amplitude. Each point was from one segment. So in each segment you have amplitudes, you have 2 amplitudes, you can multiply them, and that's the weight. So in each, to calculate an average, rather than using an unweighted average, For coherence, you use weighted average with the idea that those segments with high amplitudes, you can trust them more than those amplitudes with lower amplitudes. And this would be the result. Actually, when you look at details, for example, the points are always the same. For example, here there's some blue point here. I must do here. There's a blue point here. You can find the same point on the other side, but this point here has a very low amplitude. So really, this point here is represented by this point here. So it's the same point, but this point has low amplitude. So, and then it is down weighted. But the angles always occur. And in fact, what you see here is that if you average that, and in the end everything is normalized, it's also the coherence absolute value is also some number between 0 and 1, and you would see in this case that the coherence is larger in absolute value than phase locking. This is actually what you typically see. This doesn't mean by itself that coherence is larger just because it's bigger, but this is a typical effect. So just to also express this as equations, so we have a phase locking in the formula. This average using complex numbers is just an average of the exponent of I delta phi without weighting with amplitudes. Coherence is, you can express it in two ways. For example, if we look on the right side, this is closer to phase locking. It's also an average of the exponent of I delta phi, but it is weighted with it is weighted with the amplitudes for each segment, and you can write this easily as a second order statistics of expectation value of the product of the two complex number. For coherence, you always has to normalize. This is normalized. This is in fact power, and then this normalization then guarantees that coherence as an absolute number, absolute value is between 0 and 1. So my son is here. Okay, so that's the definition of phase locking and coherence. I want to show you a little bit what comes out in practice. So you can look at coherence and calculate it for some frequency. Actually, it's some quantity for always for pairs of sensors. So how do we display that? This is one way of displaying it. We pick some seed here in the middle, for example, at CZ, and then we calculate coherence of that seed to all other sensors, and this we display as a map. So this is what you would observe them. So it's very close. If other sensors are close to the seed, and it drops down the further you go away. This you can expect this. This by itself is not so interesting. There are also other ways of displaying that, and later I want to show a few pictures which look like that, where we show not just the result for one seed, but we show them for all seeds. So basically this picture, we show this is just one, we put here in the middle where this seed actually is. So this picture here then in the middle shows the coherence of this channel to all others. And this, for example, here on the right shows the coherence of this channel on the right to all others. This we call also head-in-head plot. Which is, so we are able to look at coherence between all pairs of channels in one picture. Okay, so this is how we look at it. Doesn't it look very interesting? And it's not interesting because what we simply observe is that neighboring sensors in EG, they are highly coherent. And if they are remote of each other, they're not coherent. So there's nothing we can learn from that. And the problem, why do we get such a result. And now I come to a second part of it. We see this because there's a problem called the problem of artifacts of volume conduction. And here I want to illustrate this. So we have, what's the problem? Say we have two sources in the brain. What we're interested in really is whether the two sources are interacting. But what we observe are two channels. Check, kannst du das bitte lassen? So eine Stunde. What we observe are two sensors, and we see an interaction between the two sensors. And when they are functionally related, it's not clear whether this actually means that the two sources are interacting. So there's one, this source maps into this sensor and into that sensor. And of course, because this source maps into both sensors, we are not really able whether a functional relation between these two sensors is caused by the mapping itself or by the true interaction. So in order to distinguish this, we must distinguish two, we must use a property which is different between true source interactions and between two mappings of the source to sensors. The difference here is the time it takes to map activity from a source to a sensor, and the time in EEG, MEG is, it's not really zero, but it's so tiny that we can approximate the time it takes to map a signal from source to sensor by zero. And this we actually exploit. So this time T1 is much smaller than the time T2. And this has some implications. I want to explain now the implications of this. Say we have one source somewhere in the middle of the brain. Just one source. And this has some activity, say a sine wave. So this means, this actually means it's deep inside the brain. So if we have just this source at this point when it's a peak, we see a positive part here and a negative part here. So what would you observe in the sensors? So say we have three sensors, a red one and a blue one and a green one, and we observe the signals there. So in the front, we see this one. We just see the same curve, just both having also the same sign. So this would be the red one and this would be the blue one. And we can also look here at this green sensor and compare with the red one. So this would be the red one, here the green one. They are identical except sign, just because there's no time delay between them. So there are only two possibilities we see. Either the phase difference is zero, in this case, or the phase difference is pi. There are no other possibilities. So we can also look at a cross spectrum, that's unnormalized coherence. In this case, cross spectrum will turn to the right, phase difference is zero. In this case, cross spectrum turns to the left, but it has no component to up and down. This is the only possibility we get. So we make an important observation quite generally. If there's one source or if they're independent sources, so independent sources do not contribute to the imaginary part of the cross spectrum. The imaginary part of the cross spectrum is this up-down direction. The real part is left-right direction. So we have, for example, for one signal, it's as I shown before, it's to the right. If there's the same sign and points to the left, if they have opposite sign, but it has no imaginary part, no component to the up-down direction here. And I just claim this here. I've shown this for one source. Even if there are many sources, it doesn't matter how many. If these sources are non-interacting, this makes second order statistic, you just get the sum in the cross spectrum. So then also the sum has no component in the imaginary direction. So this is actually, this is what you would get if you have no interacting sources. Here on the right, you see what you would expect if you have, in general, you could also have interacting sources. And then you can, so what you would measure is something like this, this would be a real measurement, some vector pointing in any direction in this complex plane. But then you know it's true interaction because it has also a component into this vertical direction. This is the imaginary part of the cross spectrum. If you normalize, it's the imaginary part of coherence. And then you can show, oh, this part must represent true interaction, and this I study further. So this is the whole point of it. I want to show you some videos where you can see this. This is in fact a real part of coherence. Real part of coherence. I show you this is a video. This is at frequency 0. I show the video up to 30 Hertz. Then it goes like this, so across frequencies. And when you look at this, you always see the same thing. It varies a little bit, but qualitatively, it's always the same. So meaning each channel is highly coherent with the neighbors and less coherent if it's remote. So when you look at this, there's not much you can learn of it because it's always the same. And this represents an artifact of volume conduction. This is our second film. What you see when you look at the imaginary part. Here at the picture right now, you see it at 0 Hertz. It's actually at 0 Hertz, it's literally mathematically 0, but this is different when you look at different frequencies. So you see this here at theta, low alpha, higher alpha, then there's nothing. Here at beta, you see again something. First of all, you see a lot of things are happening there, and this you can study. And it contains much more interesting structure than when looking at real part or absolute value of coherence. So here is now some results in practice when I look at all channel pairs. In one example, is the butterfly pod. So here's the x-axis is frequency, and for example, on the left you see the real part of coherence, and on the right you see imaginary part of coherence. Real part of coherence, you will always find, it's sometimes it would be very difficult to interpret, because neighboring channels always have a very high real part of coherence. And that would be the question, what do you get out of such a picture? In contrast, when you look at the imaginary part, then you see structures at specific rhythms come up. Here in all kinds of, this is then delta even, or theta, alpha, beta. You can see this also at gamma. That depends. It's very different across different subjects, but this shows some structure, and this you can then analyze with regard to interaction. Always just to compare this, when you show this for power, actually there are not so many curves, because this is for all channel pairs, and this is just for channel. You can see, so this rich structure you would see in imaginary part, you cannot see this in power. You just see few things which, that's not boring, of course, at 10 Hertz, strong peak, but that's about it, almost it. Then you, in this case, you see a little peak also at 20 Hertz, but that's not so interesting compared to imaginary part of coherence. So here's one experimental example. It's very old also, to show you the difference. So in this case, it's a self-paced movement every like 10 or 12 seconds. So people are asked to move the left and right hand, and they must decide when it is, and they must decide which hand. So when we look at it at the power, for example, on the left hand, we see a drop in power. So this is a left movement. When we look at C4, this is a drop in power here at 0. 0 means during the movement. This would be called ERD, event-related desynchronization. We see an increase later, a few seconds after that would be called ERS, event-related synchronization. So ERD and ERS. So this is a well-known phenomenon. And if we look at coherence between left and right electrodes, what we see here is an increase, and this is an increase increase in coherence during the movement, and where's the increase during the movement, and a decrease after the movement. And this is what's often interpreted as, you see, brain is idle, but when there's a movement, then left and right areas interact, and then it goes down again. So from an idle state during the movement, the power decreases, but the brain interaction increases. If you simulate this, simulate such a thing with non-interacting sources, you get plus background noise, you get exactly these pictures, even though the actual motor sources are non-interacting. The reason is that background noises causes very high coherence, much more or more than the actual brain sources below C3 and C4. And this background noise, if the power decreases, the background noise has a relatively large contribution, and this leads to an increase of coherence. So it's very difficult to interpret this, but just to compare with imaginary coherence, that's also difficult to interpret. What you see here in this case is actually the difference between left and right hand motor movement. You see here a difference in imaginary coherence between left and right hand movement already starting around 5 seconds before the movement. There's nothing special during the movement, but it starts already 5 seconds before the movement. The interesting thing also is it starts before them, 5 seconds before the movement, even though they have to make a self-paced movement and can decide later which hand they move. But you can still know 5 seconds, or the average at least 5 seconds before the movement, which hand they would move. And you can see this in imaginary coherence. And then you can also interpret this as there's no free will, because you know that earlier than the people do, but I don't think that's right, because they probably have decided earlier before they actually make the movement. But then it means you can see the decision to make the movement already on the average 5 seconds earlier before they actually do the movements. Okay, that was my first part. I think it was a bit shorter than I thought, but you can have here, for the second part, I would have a little break, like a 10-minute break, because I have 3 parts
Yeah, it's fine. And if you would like, we can use the time we have also to see if there are already some questions from the audience. Let's see. In the meantime, I actually have a question.
Yeah.
I may have missed it, but when you were showing the first pictures with the in which you were comparing coherence and imaginary part of coherence, I have missed what was the brain activity behind the head, let's say. Exactly.
You see the simulation or the real part?
No, the video that you just passed in the
Oh, sorry, that's resting state EEG.
Okay, perfect. Because one thing I noticed is that depending on the frequency, sometimes you have like a more for coherence rather than imaginary part of coherence. Sometimes you have more connectivity between the sensor in the back part of the head, especially this more in the lower frequency, if I remember correctly, more with coherence than with imaginary part of coherence. So you have an imbalance between which are the sensors that show a strongest connectivity with the other sensors. Is something that I have just invented, or is something that was really goes on? Like for example, in this, it's more or less all the same. But then if you go, for example, to the higher frequency, if you run the video.
Mr. Shesh, look at the film and then you show me. Show the film, right?
Yeah, exactly.
You're referring to the film.
Exactly, this one. For example, in this moment, like the sensor in the back part of the brain have less connectivity with respect to the other one. While
this one?
Yeah, exactly.
This one has less part to here or to?
No, it's more like a comparison among the wall sensor. Like for example, at the higher frequency is exactly the opposite. But it may be that it's just because it's resting state. So I was just wondering if it's
okay, if you compare frequency, I would generally say that also artifact of volume conduction, they are more pronounced at lower frequencies than at higher frequencies.
Okay.
In general, because then at higher frequencies, brain activity that goes down and there's more channel independent white noise. So that would be difficult to interpret. Exactly. Okay. So here I would be careful to interpret this as something in the which happens in the brain, but probably it wouldn't be wrong too. So I would guess that if we know the full truth at the rhythms, we would observe that higher frequencies neurons are less coherent than at lower frequencies. I guess so. Yeah.
Okay, thanks. Another quick question. Okay, there is a question from the chat from Andrea Vitale. I think that if you want, you can unmute yourself. I hope. No, okay, he can talk, so I can read the question. If I well understood, the imaginary part of coherency seems to characterize the individual frequency bands, theta, delta, alpha, much better than the power spectrum density. I guess the question is this right?
I would say, yeah, in this case, it is right. You can see, I would say you can see like effects happening at theta or at delta. You can see this easier in imaginary coherence than in power. I think that's right. In general, that's what I see. When I look at power, it's sometimes very difficult to see a peak in power, but it's often very easy to see such peak in coupling measures or in imaginary coherence. So, and if that was the question, if I understood the question, I would say, yes, that's right. In practice, you can probably have different examples and so on, but typically this is the case, in my opinion.
And do you have an intuition why?
Yeah, my intuition would be that power is, there's so much it's buried into a non-interesting signal like background noise, and this is not so interesting. But power is buried in that, and then you cannot see anything anymore. That's my intuition of it. But you cannot see the real part of coherence. You cannot see that either. You cannot see. So you're concentrating a little bit on interesting things.
That makes sense.
Excluding others which are not interesting.
That makes a lot of sense. And also Andrea Vitale, thank for the clear explanation. This is quite I guess it's something that everybody has already asked you, but I will try anyway. When you introduce coherence with respect to phase locking, you say that you weighted the points by the amplitude.
Yes.
Is there an advantage in doing that? A disadvantage? It depends on the task. What's your feeling about that? Why you weight by the amplitude?
Okay, first of all, coherence, that's a linear measure. That's an advantage in the calculation, first of all. So it's very easy to, if you know or the cross spectrum, if you know the cross spectrum in sensor space, and you have a linear inverse method, like a beamformer, you don't have to calculate raw data in source space. You can directly calculate from the cross spectrum in sensor space to source space. So that's a technical advantage. There is also if data are Gaussian distributed, this weighting is, you can show this, is statistically is the best thing you can do. That's the maximum likelihood estimator of the parameters. So weighting is statistically better. In practice, as I had, in practice, the difference is very small on sensor space. So if people weight or not, I wouldn't care so much. So if people prefer phase locking, I wouldn't object to it. That's perfectly fine. But for technical, so ideally, if it's Gaussian distributed, it is better. Also, coherence is almost always larger than phase locking, but that might be not so important. Actually, if phase differences and amplitudes were statistically independent, if they were, but they are not, if they were statistically independent, phase locking would be larger than coherence, but that's not how it is. In practice, coherence is larger than phase locking. Yeah, I mean, those are, I'm not sure if that answers the question, but...
No, it did. And I have to say that the linearity part is something that interested me a lot, because it's something that, for example, we are trying to exploit because you can actually write a forward problem in which you associate the spectrum of the data with the spectrum of the sources. And so something that as a mathematician, we are trying to do is also to try to invert that problem. That is something that is not so easy to do with phase locking value, as far as I understand.
No, not at all. That's not easy at all. And that's much easier. So linearity, one can also add that this statement, if you have independent sources, say an infinite amount of data, then imaginary part of coherence vanishes. This is, you could also say, is it also true for phase locking? But it's not. It's very difficult to find counter examples, but when you try to prove it, you will fail. There's no such proof. And then you can say, oh, why can't I find it? It looks so apparent, but it's not true. If data are nonlinear, if they're non-Gaussian distributed. So to be on the accurate side with such a argument, it would be better to use imaginary part of coherence.
Okay. Okay, so if you agree, we can proceed with the second part of your talk, and that will concern with nonlinear measure for linear data. So please go ahead.
Okay, here comes the second part. I just noticed a typo here. What we look at now is coupling. First of all, always within frequencies and not across frequencies. So I look at what happens if data are Gaussian distributed, and then they can also only be coupled within frequencies and not across frequencies. Basically, what we see here or what is possible are two kinds of coupling. One would be called amplitude coupling, shown here on the left, and the other would be called phase coupling, shown here on the right. So in amplitude coupling, you see here also red and the blue signal. The phases between them are not related at all. They're totally random. So in this case, for example, there's a big phase difference between red and blue, and a bit later they coincide. So here they are in phase, they are totally out of phase, and then this varies, can have any value. The phases are not coupled, but what is coupled are the amplitudes. So when the blue one has a high amplitude, then the red one has a high amplitude. And here it's the other way around. There's a phase coupling, but not an amplitude coupling. This means the peaks always coincide. So when the blue one has a peak, then the red one has a peak here. This is across all time, but amplitudes can be very different. Here one is small on the right, and blue one is big, red is small, and here it's actually the other way around. Amplitudes are not related, phases are related, and this can be studied, and we can in general expect that when studying amplitude coupling, we get totally different results than when studying phase coupling. So what we expect is not in general true in practice, and this is not true in particular when we have linear dynamical systems and when we have Gaussian distributed data. Now, first of all, I want to recall what we do with linear measures, what we have as linear coupling measures. And basically, it's only one, and at some frequency. And basically what you see is only that we have a cross spectrum, and that's a second order statistical moment, expectation value between the complex number z in some channel I times complex conjugate of z in some channel j. So this is again everything. This is all we have when we look at linear coupling measures in at one frequency, and we can have in general everything we construct from that. We just have the cross spectrum, and from the cross spectrum we calculate some measures. For example, to get coherence from the cross spectrum, we just take an off diagonal element and divide this by the square root of the product of the two diagonal elements. This here, this S11 and S22, these are actually the power values. So that's coherence. It's a complex number. It has a real part and an imaginary part, but importantly, we calculated it from the cross spectrum. There's one particular construction which I think is very important, at least for this part here of my presentation. That's called Lac Coherence. So you have the imaginary part of coherence, divided by the square root of 1 minus real part squared of coherence squared. This is, first of all, there many people came up with such a measure, but the first one was Roberto Pascal Marquis, to my knowledge at least, and it turned out that this construction, again, it's a linear coupling measure because it is constructed from the cross spectrum. That's a linear measure. It's actually a linear measure because if you have a linear dynamical system, then this cross spectrum determines all statistical properties. And that's why this is called a linear measure, even though it's a second order statistical moment. But for linear systems, second order statistical moments completely determine statistical properties. Now, and this is what we discussed there shortly before, there is, first of all, there's a technical advantage if you have a linear measure. Typically, we also have linear inverse methods. It's like a beamformer, for example, is effectively like that. Even though it's a linear measure and it's a linear filter. The construction of the filter, then it's also contains a nonlinear part. But once you have a filter, you map the data by linear applying this filter. And for a second order statistical moment, like a cross spectrum, you must apply this filter both on the left and on the right. So when you have a cross spectrum in sensor space, you apply the filter on the left, on the right, and then you get the cross spectrum in source space. This makes it very simple, extremely easy to calculate. So that's a real advantage of linear measures. One can also add that for linear measures, if you have independent sources, like in the cross spectrum, they always add up. And this additivity is not true for nonlinear measures. One should say it's not true for nonlinear measures above statistical order of 3. So for order 4, it's not true anymore. For order 3, it's still true. Anyway, it's an advantage. It's much simpler to use a linear coupling measure. And then when you decide you want to use a nonlinear coupling measure, you should have a good reason that you see something you cannot see using the linear coupling measure. And in general, this will not be the case if you have linear dynamical systems or Gaussian distributed. So Gaussian distributed data. Gaussian distributed data are very important in practice. Data we measure are not perfectly Gaussian distributed, but they are approximately Gaussian distributed. So the whole idea of Gaussian distribution is very important for us. We can have various forms where this can be important. For example, we look at empirical data. So here, this is just an example of some filtered empirical data, and this is what they look in the time domain. And here is when I look at the distribution of the data, almost perfectly Gaussian distributed. They are not always like that. Sometimes they deviate more. So I've shown you here an example where this is almost perfectly the case, but usually Gaussian distributed is a good approximation, and therefore it matters. It matters also when we use in any kind of model. When we use not any kind of model, when we use a linear model, often we use we try to fit a linear model, an autoregressive model, to interpret the data. Then, so we have data fit an autoregressive model, and then we interpret the coefficients, the AR coefficient of the model. So this model technically always gives Gaussian distributed data. So basically when we say, oh, we fit the data with an AR model and interpret that, then we effectively assume it's Gaussian distributed because this is what the model says. So we implicitly, in many cases, also with Granger causality, for example, directed transfer function, partial coherence, we all, not partial coherence, partial direct coherence, or what was that called? We always assume that data can be modeled with a linear model, which gives Gaussian distributed data. Also, Gaussian distribution matters because sometimes, and this is one special point here, we have some measure and then we interpret it in the way and say, oh, the interpretation is only valid if it's Gaussian distributed. Then one must say, well, then one should check whether it's Gaussian distributed. At least it matters in the sense that for some interpretations, we assume it is Gaussian distributed. Okay, so therefore it matters. Now, what's the consequence? If something is Gaussian distributed, so I'll write it here, the probability distribution of, say, I write this here in a complex way, say Z here are the data in the complex Fourier domain at some frequency. So Z here is a vector, and you can write the distribution in this way: exponent minus Z conjugate transposed, some matrix, the inverse Z. In general, this matrix is the cross spectrum. But here in the following, I always assume that data are normalized to power 1. So for the analysis of coupling measures, at least what I do here, it really doesn't mean, it doesn't make any difference. So power is always 1. And in this case, the only free parameter here, that's for 2 channels, this would be coherence. So power, this is what you see in the diagram, is 1, and you see 1 complex number, that's coherence, and that determines the entire distribution of my data in the complex Fourier domain. So if we in some cases Gaussian distributed, if we know this one number coherence, we know anything, because if we know coherence, we know the distribution. And if we know the distribution, we can just calculate any expectation value. And coupling measures are always some kind of expectation value. So there must be a relation between a nonlinear measure and coherence for Gaussian distributed data. This is not new in a formal way, but then the question, what is new, perhaps relatively new at least, is what are these relations? And this is one study where we went through all these nonlinear measures and asked the question, what's the relation to coherence if we have a linear dynamical system, or if we have Gaussian distributed data? So here I want to go through a list of coupling measures we actually have. This is one relatively wide used measure, and it's a nice measure, but still it has some relation. So that's called the weighted phase lag index. That's imaginary part of the cross spectrum divided by the expectation value of, sometimes the mouse is strange, expectation value of the absolute value of it. So the numerator of it is just the imaginary part of the cross spectrum, like for imaginary coherence, but the normalization is different. For imaginary coherence, this here would be power, but here it is different. So what's the relation for that? For Gaussian distributed data, it looks like that. It's some specific function of Lac coherence. So TLDI, Lac coherence by this measure by Roberto Pascal Marquis. And let me first illustrate what this means. It is a function of it. So it is a function of Lac coherence, means weighted phase-lag index is not a function of imaginary coherence. It's a function of Lac coherence. And that's the difference. So to illustrate this is a simulation. Linear dynamical systems, they are simulated. Each point here is one dynamical system, totally arbitrary. And for the system, we calculate imaginary coherence and the weighted phase-lag index. And this is on the left, you see what comes out. Now there's, you would see, they are a little bit related, but not perfectly. So if we know imaginary part of coherence, we don't know weighted phase-lag index. We have an idea about it, but we don't really know it. But this is, so weighted phase-lag index is not a function of imaginary coherence, but weighted phase-lag is a function of Lac coherence. So if we plot them directly, we get such a curve. They are uniquely on one specific curve. And if sometimes we can just see that this is a curve, but if we know the functional relationship and insert it, they're just identical. So if we could as well for linear dynamical system calculate Lac coherence, use this formula, and then we get the weighted phase-lag index. Actually, this is perfectly true for infinite amount of data, but if they're finite, there's almost no difference there too. But if we have this case, then we should ask the question, is it worth to calculate a nonlinear measure when we directly might as well calculate the linear measure? So that would be the question. I want to go through a couple of measures, just present you the results for that. So the first was the weighted phase-lag index. We can also do this for the phase-lag index, also called PLI by K. Stam, the first author there. And then we can see for Gaussian distributed data, phase-lag index is identical to Lac coherence. Again, what we observe, it's not imaginary coherence, it's Lac coherence. So this plays, Lac coherence, in this kind of view, plays a relatively important role here. It's not always Lac coherence. Sometimes for phase locking itself, it's a bit complicated. But we can also do this. So basically, phase locking value, what I explained before, is the same as complex numbers. It's the same as coherence plus a little scaling function, and this is to really excellent approximation. We can also write an analytic, an exact relation for that as an infinite series, but to excellent approximation, we have a little scale function for that. But in fact, for phase locking value and coherence, the relation, that's not so interesting in practice, because you can do either way. It doesn't make a big difference anyway. So, but what is important conceptually, I would say, is more when we compare amplitude coupling to phase coupling. So this is amplitude coupling written in this way. There are variants of it, but basically, say we have the correlation of, in fact, here written the correlation between two amplitude squares. So this I would call here back phase envelope coupling. And then, so this does not depend on phase difference at all. But if it's a linear dynamical system, amplitude coupling is identical to absolute value of coherence square. In principle, just make it just a conceptual point. This itself is also a unique function of phase locking value. So amplitude coupling completely determines phase coupling. and vice versa for linear dynamical system. Then the question, generally the question is, say we look at amplitude coupling in data. Do we really see something different than when looking at phase-phase coupling? It can be the case. If we see something, then it's not a nonlinear system. If it's a linear system, no, we don't see anything else there. Finally, there's a version, I would say, orthogonalized power envelope correlation. This is sometimes used. People want to calculate power correlations between sources and want to correct for artifacts of volume conduction, and this is one version of it. You could use that, and here I give you a report that, so this version, you calculate amplitude coupling, correct for artifacts of volume conduction, and what you get, and this this form I call here OPEC. It's the same as Lac Coherence squared actually. So again, the Lac Coherence plays an important role in also in this case. Okay, but what I would say here, I will later say this again, the important point is that people who do this, who calculate this measure, they assume it's Gaussian distributed, because otherwise the correction, the point that this is corrected for artifact of volume conduction is not true. Then the question is, but if you assume it's Gaussian distributed, why don't you calculate this quantity on the right in the first place? Okay, to show you some results for that, simulated and real. So this is, this would be, for example, simulated linear systems, random linear system, each point is one system, a linear system, and a highly nonlinear Kuwamoto model. That's just an interaction between phases. Details are not so important. It's just phase dynamics, which is then translated to a signal. So the red points are Kuwamoto, blue points are linear system. So we have here on the x-axis, we always have a model. Model means, we calculate coherence, and for a specific quantity, we use the formula. So we say, we assume that the formula is correct, and then we, for example, we calculate Lac coherence, and we have a specific formula to calculate what we expect for weighted phase lag index if it's a linear system. That's the value here on the x-axis. On the y-axis is the actual value for the nonlinear measure. And we see here for linear models, they are always, for all measures here considered, they're always almost exactly on the diagonal. But if the system is nonlinear, we can have deviations. These deviations are relatively small for the Kuwamoto model, also relatively small when we look at phase-phase coupling measures, nonlinear phase-phase coupling. But as soon as we look at amplitude coupling, then these deviations can be massive. Here is some results on empirical data, resting state data, where we always looked. This is actually this one subject and one frequency for all channel pairs, if I recall right. So resting state EEG data, empirical data, we look at our model and the actual nonlinear coupling. So for weighted phase lag index, there's almost no difference. And as you can see this, and I would say entirely almost through all data. For other phase measures like phase lag index, PLV, or imaginary PLV, there are differences, but they are not so big. The really interesting part, I would say, is, to my opinion, amplitude coupling. That is different from the model. So amplitude coupling is almost always larger than what you would expect for linear dynamical systems, and this is worth studying. Also, to come finally to this orthogonalized version of amplitude coupling called OPEC here, the model cannot explain the actual value, can explain not at all. So this means with respect to this model, assuming that data are Gaussian distributed would be completely off. This is not verified from the data. And then you have, of course, a problem if you say, oh, for my interpretation, I need to assume it's Gaussian distributed. Okay, so I would say, yeah, this is the basic conclusion of it, almost all, so this is the conclusion. And I have one more slide here. Next one. This is some example for ferret data, invasive. An average, there are sometimes they are awake or REM sleep, and sometimes they have slow wave sleep. And this is, we looked at time period slow wave sleep versus non-slow wave sleep, and calculated coherence between all sensor pairs, or an average that. And this would be, you see, the function of coherence, and there you see almost no difference between slow wave sleep and non-slow wave sleep. But when we look at the nonlinear part of it, we see very high, very clear difference. So the nonlinear interaction, it's a nonlinear interaction which distinguishes slow wave sleep from other periods, but with linear measures, you do not see this. Therefore, it is also worth to look at amplitude coupling. So it's published here. Now I want to finish this part. Okay, that was it for this part. I have a third part, but now I stop. You can have questions, and then we have another break. Is that right?
Yeah, thank you very much. Very, very interesting and talk. Let's see if there are any questions from the audience. Let's check. There is a question by Alberto. I think he can unmute himself. I hope. Yes.
Yes. Can you hear me? Yeah. Thank you, Guido. Very, very, very interesting. So I was wondering, because so there are many different models that one can use to, let's say, simulate or to generate signals that can try to simulate to some extent brain activity. And now you showed us this Kuramoto model, but I was wondering, are there like, well, not gold standard, but what would you consider as realistic as possible model for brain activity in terms of, I would say, its frequency content and also its linear or non-linear behavior, if the question makes sense.
Yes, it makes sense, and we wonder often ourselves what to do. Depends on what you want to see. If you look at cross-frequency coupling, and then AI models don't make any sense at all, of course. And yeah, is there a general answer to that? I don't think so. I was always lately looking at some models, also Kuramoto models, other models, Breakspear for resting state alpha, to show long-range temporal correlation, you see in DFA analysis. But it's very difficult to do that, to find that. So yes, you have a very good question, but I do not have a good answer to that, because often I want to look at some aspects of data I see, then I see, does this model explain such aspects? Then I see, oh no, it doesn't, not at all, not when you look at this property, like long-range temporal correlation. It doesn't look like real data, barely. And then, therefore, I don't think that Kuramoto model is a good model at all. For example, amplitude coupling for Kuramoto model, it's totally low. It's lower than you expect from a linear model, but in empirical data, it's larger than you expected from empirical data. So to study amplitude coupling as a nonlinear phenomenon, I would say Kuramoto model makes no sense, at least not what I've seen so far. Yeah, that's a long, bad answer to a short, good question.
No. It's a very, very good answer. Thank you. So let me also try this one. So suppose you want to validate a pipeline for connectivity analysis. So so my question would be, what would you use? And I try to also answer, like, first, depending on what you want to see, you can use different models. And if you want to try and validate something as general as possible, you use all of them, right? So you try with many different models rather than one.
To validate,
or maybe it is the question itself
that's true. You can that's true. You can look at all kinds. I think that makes sense to look at all kinds of models, linear and nonlinear, and to see whether your analysis you can. This is usually you come up with a new method and you say, "Oh, I show it works on simulation," but what do you simulate? And
exactly.
You can always simulate something that your method is best, always.
That's always the best idea, yeah.
Yeah, and then, okay, yes, sometimes in this regard, yeah, I would say it's not a really formal criterion, but just try to be a little bit honest about it. So if you think, try a little bit to think, when does it go wrong? And just be inventive to find when it goes wrong, and then to see where the limitations are. This is how I would do it.
Yeah, I see. Okay, yeah, thanks a lot.
We have a question from Marco Congedo. I think, Marco, you can unmute yourself.
Yeah, can you hear me?
Yes.
Yeah, hi Guido. I just wanted to say that I like very much what you do, and I follow your research very closely. My question I could not follow the first part of the presentation, so I apologize if you already say that. Okay, but my question is about the difference between imaginary coherence that you defined and the lagged coherence defined by Pasquale-Marchi. So is that correct to say, according to you, that imaginary coherence is sensitive only to asynchronous synchronization, whereas lagged coherence is sensitive to all but synchronous synchronization? I mean, to everything that is not exactly synchronous.
No, I would not say that, I must say. In this say, they have some different properties, but I don't think that the difference is in practice so important. They both are non-vanishing. If the values are non-vanishing, then it can't be that all sources are non-interacting. This is what they have in common, and there's nothing more you can say about it. Both, so imaginary coherence, you could say, it only sees it if things are perfectly out of synchronization, or like in 20 degrees. No, that's not true. Also imaginary, if they have like a phase degree of 30 degrees, for example, phase delay, or even lower than that, you both measures see that in principle.
Well, that's not what I saw in some simulations I did. That's why I'm asking you the question. But if you say that you've seen something different, okay, I understand.
Well, you can. Yeah, I'm not exactly sure. But say you have a 45-degree phase difference.
Yeah.
Then imaginary part of coherence, like Lac Coherence, they are not small. It's not that they are close to zero. I mean, if you have 5 degrees phase difference, then they're small, but 45 degrees phase difference leads to a large imaginary. It's just a projection. So and 45 degrees has a relatively large projection.
Okay.
Sometimes a Lac coherence has a very nice property. Its actual value, if you have two sources and two channels, the value is independent how you mix the sources into senses. And that is what imaginary coherence has not. For imaginary coherence, you could say, if it's non-zero, they must be interacting. This you can say. But what's the value of it? This can depend how they are mapped. And this is not the case for Lac coherence. So this is theoretically a nice property of it. This is also the case for weighted phase lag index. It's a bit the use, but this is only true for two sources. But in brain, you do not have only two sources. So it's a bit limited value. But I like this, the theoretical part of it, even though probably it's not so that you gain so much from it.
I see. Okay, thanks.
We have a question also from Laura. Laura, please, if you can unmute yourself.
Thanks. Yes, I think it's working.
It is.
So Guido, I wanted to ask you two things. One is regarding to the very last part of what you just showed. So the basically the power envelope correlation that you made use of to contrast the slow wave sleep data and the non-slow wave sleep. So basically in that case, like, are you exploiting the contrast between the two conditions to avoid artifacts of volume conduction to appear in your results? And if that is the case, I mean, would this be the solution that you recommend if you have two conditions and maybe power is equal across the two conditions, or how to use the power envelope correlation without the orthogonalization if you have only resting state data or something like that?
Yes, good question. This is similar as before. Good question, no good answer. Or the answer is like this. No, in this case, there was no correction for artifacts of volume conduction. First of all, I just look at, do I see a difference? Where does it come from? I don't know. It is certainly nonlinear. I see a clear nonlinear effect. There's a difference. What part of this is artifact of volume conduction and not? Is it a mixture or not? Probably partly or not. But that I do not know. I have this not corrected. Is there a way to correct it properly? To my opinion, I don't know a good way. I think Karim, you see, probably not here. There's one paper who does it, to my opinion, properly, but I'm not sure if you see if it works for within frequency. I think it only works for cross frequency. But all I presented here was either not corrected at all, like power envelope correction, not corrected at all, what I've shown, or the claim that it's a correction is not really accurate. It's not an accurate claim. And therefore, to your good question, I again do not have a satisfactory answer, and I would suggest to do some work on the theory for it.
Okay, thanks. And then the second question is, you know that these orthogonalization procedures are becoming common also in like phase locking metrics, like there is an orthogonalized version of the PLV. And so I was wondering whether also, I guess that given that the strategy for the orthogonalization is the very same, whether the implicit Gaussianity assumption also affects the results for the PLV.
Well, PLV, I haven't seen this for PLV itself. Why is that necessary? I mean, you could also just calculate PLV as the complex number, use the imaginary part. That's has been suggested, I think, by 3 people independently of each other, and that's, to my opinion, it's fine in practice. In theory, you could say, you could have exceptions when it doesn't work, but in practice, to my opinion, that's fine. To use PLV together with orthogonalization, I haven't seen this, and I'm not sure.
No, I have. I don't remember the first author, but it's something that someone. I mean, I have seen it. I don't remember the first author, but there is someone who has come out with this orthogonalized PLV. I think that's maybe also because these measures are also used in the, like with Hilbert transform and not only with the Fourier transform.
Okay, do you think there's anything better than just using imaginary PLV?
No, but to my experience on the data, the results are not really, are similar, but not really the same. So I was wondering whether there is some, I don't know, real part that gets back into this orthogonalized thing and so on.
Yeah, I think there's one in general thing, this orthogonalization. This is a bit like this orthogonalization works only for Gaussian distributed data. And also written this in the paper. This is really, otherwise the whole concept, because when you use this orthogonalization, you remove linear dependencies. That's you orthogonalize with some linear transformation. You remove a linear dependency, but that doesn't mean if data are not linear, removing a linear dependency doesn't mean data are, say, then they are independent of each other. This is what ICA exploits. The whole ICA is based on this observation that removing a linear dependency doesn't make, also as an artifact of volume function, doesn't make the data independent. Also as an artifact of volume function, removing a linear dependency is not enough. And that's how ICA is constructed. It says there were, to get it, to really make an ICA deconvolution, we exploit the non-linearity of the data to get more information. And therefore the whole orthogonalization approach is in general only valid if data are Gaussian distributed. And if they are Gaussian distributed, then why don't you just look at coherence? What's the point?
Okay, thanks.
Thank you very much for this inspiring talk and discussion.
Hi, can I in the meantime also ask a quick question?
Sure, Maria, please go ahead.
Is it theoretically possible to see the volume conduction in the sensor data not as 0 pi, for example, I don't know, from mixing with other sources or something? Sorry, I'm muted.
Guido, I think you are muted.
Okay, yes, okay. No, it's always from 0 to pi. Well, that's volume conduction. If it's something in between, it's not volume conduction, or not only volume conduction at least.
Yeah, so it could be like a mixed with something else, and then it shifts a little bit the phase.
Yes, yes, yes. If you have a real interaction plus volume conduction, that affects the phase.
Okay.
But if it's different from 0 or pi, at least there must be something in there which is true interaction.
Okay, let's go.
Then I start. So this is about cross-frequency coupling, in particular phase amplitude coupling. But in principle, you could also have cross-frequency with amplitude, but here it's about phase amplitude coupling. So I must see whether, whoops, no, I can't. Okay, so we have just one thing here. So we looked at, first of all, to recall actually. So this phase coupling here, amplitudes are arbitrary, but they're always in phase. The peaks are always at the same time. So that's phase coupling. You can have it at phase locking or coherence or many other measures. This phase coupling is always at the same frequency. It's not between different frequencies. Sometimes I must. So this would be amplitude coupling. Phases are arbitrary, but here, but amplitudes are not. When the red one is high, the blue one is higher. When red channel is low, blue channel is low, but phases are arbitrary. Phases are arbitrary in this case. In principle, amplitude coupling is also across different frequencies. I've seen, perhaps you have different experiences, but I've seen that in practice, amplitude coupling, you can almost always see only within frequency and not across, but you might have different experience. But here I look at a different thing, and that's phase amplitude coupling. So, and this would be the classical situation of this. So we have a low frequency part, like I would call this theta here, but it doesn't have to be theta, of course. But here it's a low frequency theta amplitude and some high frequency, say gamma part. The phase of the high frequency is totally random, at least compared to the theta rhythm, but the amplitude is not. When here the phase is when here it's up, when you have a peak in this theta signal, then the amplitude of the high frequency part always has a peak. Not the gamma itself, but the amplitude of gamma. That is also has also a peak, and that we can measure. There are typically two ways to address this. One are, I would call here, classical PAC measures, phase amplitude coupling measures, and bicoherence. So I would say probably 95% or 99% of the people would use classical measures. I personally prefer bicoherence, and here I present relations between them and tell you why I prefer bicoherence. So first of all, let's look at classical phase amplitude coupling. And so what we have, first of all, what we need is to have a signal. So this blue one, that would be here, for example, filter. That's a simulation here, but would be, for example, the filtered data in the gamma range. We see here burst and later the burst, but we are interested in the amplitude of that. The amplitude of that would be the red curve here. And technically, what is done is we have the data, filter the data, then we get this blue curves, make a Hilbert transformation that gives a complex function. We take an absolute value, and that gives the amplitude. So this is how the Hilbert transformation can be calculated. It's very easy. I find in most of the papers it's written as some singular integral over time. That's really not necessary. That's a continuous representation, which we don't do for discrete data anyway. So the Hilbert transformation does that. So for example, what is shown here, the bottom, this blue line, that's our filtered signal. And this filtered signal, from this filtered signal, we calculate a complex signal. This way, this is this in the complex plane, it would be a rotation. The point, and this is how it is constructed. This is rotated, always that only using only positive frequencies, not negative frequencies. And the real part is the same as the original signal. And then we get an imaginary part. And that's actually really this imaginary part of this, it's really the Hilbert transform. Actually, if you do it in MATLAB, you get some complex function. So basically what you do in MATLAB is like this. You take your data, make a Fourier transformation, then you set all negative frequencies to 0, multiply positive frequencies by a factor 2, and then you make an inverse Fourier transformation. This means you explain the data with only positive frequencies. Then you get a rotation here, and this is then the complex Hilbert transform. And that we take as the amplitude of that is then the amplitude we analyze further. You can also use this to calculate an instantaneous phase to do whatever analysis you want to do, which is also often done. So This is a Hilbert transform. And then we need to calculate our phase amplitude coupling. First of all, when you do a Hilbert transform, I started with you filter the data. How do you filter the data? You do this in some band, say gamma, between, don't know, 30 and 40 or 30 and 50 for low gamma. And it's very important how big your band is. It's an important issue in the whole analysis of phase amplitude coupling. Here I want to explain this qualitatively, why it is important, why the bandwidth is important. So basically, we have this blue line here, that's our low frequency range. And then at some points, it is high, or theta, at some points it's low. Now we want to see whether the amplitude of gamma relates to this. This means we need some temporal information about the amplitude of gamma. And this temporal information must be relatively localized. So if we smear it across all time, then the temporal information of the amplitude of gamma that gets lost. So I want to illustrate this. So blue is low frequency theta, red is filtered gamma. So in this case, we use a wide filter, and then we have, it's relatively sharp in the time domain. And then we can, in this case, we could say, or it's very relatively easy to say that the amplitude here coincides with theta. If we use a very narrow band gamma, then more, and it depends on how narrow it is, the narrower it is, the more the temporal information is smeared across time, and it's very difficult to see, at least compared to that, we cannot see so much difference as it varies across time. When we have a very narrow band, we cannot see anymore that it varies across time. And therefore, it must be limited. It cannot be arbitrarily narrow. So this is why the bandwidth is important, because we also need the temporal information, which might get lost. This is now the idea how phase amplitude coupling is typically calculated. There are different ways of it, but basically, this is basically it. So this is a situation we have. There's a high frequency part here. This is the blue one, gamma, say. This is, and here we have a low frequency part. This is green here. That's a theta. And then, but what we observe is the sum. That's our data. We have in one channel, it's the sum of the theta and the gamma, and that would look like that. Of course, we can reconstruct high and low frequency part by respective filters, but what we observe is the sum, and then we reconstruct the separated parts. And then what we do for phase amplitude coupling is we analyze these separate parts. So first, let's think, what do we get if we divide the data into segments and we calculate for each segment the phase of theta, completely ignoring gamma at all. We calculate the phase of theta, represent the phase as a point on the circle, then it would look like that. So they are randomly placed because this is, say, it's resting state. Where we place the segment doesn't matter at all. So it's randomly placed, and if we average all these blue points, we get a very small vector here. The theta phase by itself is random. But this would look different if we, for each segment, we weight the theta phase with the gamma amplitude. Then it would look like that. So sometimes when the theta phase is, say, close to pi, so here on the left side, it happens that the amplitude is very small. If phase is close to 0, so they coincide here, amplitude is large when it's on the peak. If phase is close to 0, then gamma amplitude is very high. And then and this is what we then use, and so we average the phases of theta weighted with the amplitudes of gamma. And in this case, what we then get is it's not so big in this case, but typically we get phase amplitude coupling. That's the length of this average then here, and that's at least substantially larger than 0. So this would be a formula for that. We have here this sometimes the mouse doesn't work very well. Yeah, I don't know. So on the right we see exponent I delta phi. These are the points on the circle weighted with the amplitude of gamma. Now I can't see my own mouse anymore, and I don't know why. Okay, so this would be called the mean vector length. And so this is a measure of PAC. There are also other measures. So mean vector length would be the one by Nolte. This is here shown in the middle. I cannot see my mouse anyway. I don't know.
Maybe you can try to stop the slideshow and reopen it. Try to close the slideshow and reopen it and see if you can see it. Okay, now I can see your mouse actually. Okay, so now you can. I can see your mouse.
Can you see my mouse? I can't see my mouse.
Yeah, is right on the right.
It's not moving. But I'm. I could try. Do we have 1 minute? I'll try a different mouse. Perhaps it's the mouse.
Yeah.
Okay. Yeah. Okay.
Let's try.
Okay, now the mouse moves, right?
Yeah, and we can see it.
Like the behavior of this mouse. Now the mouse moves. And okay.
Yes.
All right. So in the middle, this was I explained before. That's the method of Nolte, a different way of doing this, but probably conceptually, probably you think it's very different, but it's not really. That is, you have an amplitude of gamma and a low frequency signal, and then you calculate phase locking. You could also do coherence of then you calculate phase locking between the gamma amplitude and the theta signal at the theta frequency. This is phase locking. Actually, it's a little bit weight how it's differently weighted, but in fact, in practice, almost the same. So I would refer to the Nolte measure here. A different way suggested by Tort. It's quite interesting. That is really conceptually also different. That's modulation index. Then you look at the distribution of phases. You look at the distribution of phases and you weight the distribution with the amplitude for each phase. And then you see how this weighted distribution compares to a uniform distribution. And for example, if there's no relation, you would expect a uniform distribution, but in practice, or if there's something in the data, you would see a deviation from the uniform distribution. Conceptually, the difference is that here, it could happen, for example, here in this case, for the Nolte measures, that there is a relation, but it's like biphasic. Say, sometimes you can have dots on the left, on the right, but not up and not on the vertical axis. And this would mean that here you would see a difference from form distribution with 2 peaks. And this you could not see with a Carnoti measure, but you could see with a torque measure. So, but in practice, it turns out that most of them, they just have, either there's nothing or you just have a single peak. And when you only have a single peak, probably this measure is better. So even though there could be cases where torque measure is better, in practice, I think that the Carnoti measure is better. Now, that was phase amplitude coupling. Now I want to talk a little bit about non-stationarities. That's important in particular to understand bicoherence. Say typically what we have, so it's a kind of a different topic. Say we see this kind of signal in the data. So it sometimes it jumps up, then it goes down, jumps up. And when you show such a signal to data, I think most people would agree that this is, it's a non-stationarity. But that's not really the case. So in fact, in this case, it was a model. It was a model data by a completely stationary model, no explicit time dependence. So this was just the movement of a particle in a double well potential. And the force of it is a derivative, actually. It's a nonlinear function because this was the 4th order point. The particle, sometimes it's here, and then by coincidence, it jumps to the other side and jumps back. And this is the signal you get there. So this equation of motion, so you get the structure not because there's a non-stationarity in there, but because there's a nonlinearity in there. So the force of this is not a linear function of the position. That makes a nonlinear equation of motion in this case. But to say again, this is a stationary equation. So to really understand this, one should actually recall what it means if something is stationary. What's the definition of something being stationary? A system is stationary if the statistical moments do not depend on time. For example, you take the variance, expectation value of the variance, a function of time, and this is constant, it does not depend on time. Then stationary is more than that, also refers to higher order moments, but that's in principle what stationarity means. Now we can say, let's see whether we observe this in data. And then we calculate this, and then we see whether it's constant or not. Here's what sometimes people looks like they do, or sometimes also see this. Say, okay, let's see whether this is the case. So we have here some data, make a sliding window, and in this sliding window, we calculate the variance, and S of t means the center of the window. So if we do that, we would come up with a function like that. So this would be then the red curve. That's the variance as a function of time. So that's, you see, it depends on time. So it's not stationary. Would be the at least naive conclusion. But in this case, actually, what was done is it was modeled with stationary white noise, and you still come up with that. Now, there was something you did wrong in this analysis, namely it was to confuse an expectation value with an estimator of the expectation value. You just see a statistical fluctuation. So basically, to decide whether a variance at some point, depends on time or not, you must really, at least conceptually, decide what it actually means in some expectation value at some time point. So, in fact, the variance at some time point, actually you must have some kind of ensemble. When you say, this is my statistical moment at that time point, you must at least define what an ensemble is. How do you repeat the time point? You must, for this, you must have some kind of clock. So when you have, for spontaneous data, the expectation value at some time point has really no meaning, because you have no way of repeating the time point. You do have, you can repeat something if you have a stimulus. You can present a stimulus 100 times, and then you see, then you get an ensemble, at least roughly. Then you can do some statistics. But for spontaneous data, the whole notion of ensemble is meaningless. You only have the data once and not many times. It has no statistics at all. So this is what I mean. The notion of non-stationarity requires a clock. It must be, you must say, oh, the statistics varies in time relative to the time of the clock. That can be a stimulus. That can be also the start of the measurement. You have many times, like drying out of electrode. But when you don't mean that, then spontaneous data, they are stationary, but because this is what stationarity means. So what are the consequences? What you have if you have a stationary situation? I want to show this for to show this for one case and to study. We look at phase locking value or coherence always within frequency, never across frequency. Why don't we? Why don't we calculate coherence between, just using the same formula, just we take signal at different channels at different frequencies. We can do this formally, but we never do this. So why don't we do this? The reason is actually that coherence always would, the formula, if just insert, vanishes if the two frequencies are different for stationary systems. This I want to illustrate a little bit. So it's not that we couldn't calculate coherence across frequency, it's just nothing comes out. And let me show this in this case. So for this case, I calculate a linear, what I would call it, linear CFC. That means this is linear cross-frequency coherence. So I use the formula for coherence, but I just apply it across frequencies. So this would be, for example, if we do this, here again, here, sometimes here, what I simulate here is, it has a clock. I simulate an event-related potential, and this is repeated many times in many trials. And if I show the signal across all trials and a function of times in this kind of plot, it's always the same thing. So this clearly has a non-stationarity, because relative to time it differs like 100 milliseconds before the stimulus or at or after that. And for this, we could calculate this linear cross-frequency coherence. And if we would do it like that, we would get such a result. And this is actually the same signal between two channels. And then we would get such linear cross-frequency coherence. We get a non-vanishing result also when the two frequencies are not the same. So now I make a little modification of this. Here I have, oh sorry, it's just one second. It's not two channels, it's just one channel. We take the same signal at different frequencies from the one channel. So now I have here, make a little modification of that. And here I say you made something wrong with your clock. Your clock is wrong. It's one sample too late, or one sample longer than the actual delay was. Then your result would look like that. So it has a clock, but you don't know the clock. In principle, the brain said, yeah, spontaneous brain activity. It has a clock, but you just don't know the clock. So, but this is a simulation where you have a clock, but you have it wrong. In this case, when you calculate cross-frequency coherence, any coupling between different frequencies, it would always it would always vanish. Here, this mouse is a little bit strange, I must say. So that would always vanish here, what you see here on the right. So for non-stationary systems, to see any non-stationarity there, it's not enough that it has a clock. You must also know a clock. And if you don't know any clock, then you can just consider that as stationary data. It just is stationary because you don't know the clock. So then here, is it just a question of terminology? First of all, whether you call something which I would say it's nonlinear, and then you call it non-stationary. So perhaps you say, oh, it doesn't matter. First of all, it matters, this aspect, for bicoherence. I explain this later. Often you can hear something like this in paper. So a reviewer would write, you assume stationarity, but that's not correct. Often I would say, in this case, I would say, but it is stationary. Resting states are stationary. So the whole criticism that you must address this, that something is not stationary, that's not correct. You can consider a resting state data as stationary. Often you can also do something like this: as you overinterpret your result, you make some estimate over a sliding window. Then you see variation, and you say, we have non-stationary. We observe a non-stationarity, but it's not really what it means. It just it's a statistical variation of some estimator. Doesn't mean it doesn't really mean anything. For stationary linear systems, you would expect also the same. So it distracts from really interesting phenomena like switching in the brain. Finally, I would say that it's not so important to really to see second by second what the state is, but in the end you want to have a dynamical law, and this dynamical law is something static. The law according to which brain we have, that's the same now and tomorrow, and if the law would be different by the time the paper is published, would it be worth? So you want to have something, a dynamical law, and that's the same. Okay, I'm not sure if that was clear. Now I come back to bicoherence, or I come back to cross-free.
Sorry for interrupt. There are 5 minutes left, more or less, if this is okay for you. Not much.
Huh? Yeah, of course. But then I must switch some parts. I cannot do this in 5 minutes. It would take much.
Okay, I mean.
I shorten it. I understand. I don't want to go.
Okay, I mean, it's not strict if are 6 or 10 minutes. It's not a problem, but just try to conclude.
Yeah, I understand, but it just happened that it took so long. Okay, then I must shorten many slides, but I will shorten them. I don't want to. Do not extend it. Okay.
Okay. Thank you.
Okay, and then all the derivations I skip. Just let me explain what bicoherence is. So for the cross spectrum, this was a recall what the cross spectrum is. A cross spectrum is calculated at some complex number where you have 2 signals, but you take them as the same frequencies. You do not look at different frequencies, because if they are stationary, there's nothing you can see at different frequencies. That's a consequence of stationarity. Bicoherence, or bispectrum, unnormalized version, is one statistical order higher. So basically you have 3 signals, but there's a constraint on the frequency. The third one, frequency of the third, is the sum of the other 2. This is also the case here. The second is the sum of the other one, but there's only one, so just one frequency. So bicoherence, formally it's at 3 frequencies, but for stationary data, then you can make a constraint. Then you only look at the cases where the third frequency is the sum of the first 2. And that's what bicoherence looks at. Otherwise, it's Lac coherence, except that it is written as a coupling at two frequencies, but it really means a coupling between three frequencies, F1, F2, and the sum. So basically, then you would get pictures like phase amplitude coupling. They look the same, but you think it's calculated totally differently. But first of all, they look the same. You just have two frequencies. One say low, but it can also be high, like low frequency, high frequency, and we get some coupling. So this is a picture what we would see typically for alpha. Pictures look similar to phase amplitude coupling, and because I show you some. This is typically bicoherence at some channel. You could also look like that. That's a heart artifact, for example. This is a muscle artifact. This is something weird. I don't know what this strange muscle artifact. You can see that sometimes that I don't understand. But anyway, so this is actually a strange artifact across many channels. That's important. Important now is pictures are kind of similar to PAC, but it seems that they mean something totally different. And okay, I must skip so much that I just show you some. I want to explain what I want to explain here is that first of all, there are theoretical reasons why they are not so different at all. For example, if I look at the same thing, this in a simulation, phase amplitude coupling on the left, bicoherence on the right, you see this is almost the same. You see this here on the lower right, but this by construction doesn't really mean that it's different. But basically, PAC and bicoherence, you get the same result, more or less. And there's also a reason for this in the theory, but I must skip this. So, I skipped the entire explanation. Why it is the same, but I'll show you some results. This is also for a simulation. In some result, you would see two narrow peaks. For whatever simulation, when we do this with PAC, use some kind of more or less filter as wide as the low frequency. We also get these two peaks. They're actually the same. The shift has no meaning really. That's a convention question. You see two peaks here for PAC and bicoherence. You see the same peaks. But if you use PAC with a wide filter, so gamma filter is twice as wide as low filter, and I would recommend not to do this. You see PAC as a smeared version of bicoherence. So the point I want to make it is, in general, PAC is a smeared version of bicoherence, and if you do PAC, I would call, if you do it properly, then PAC and bicoherence are the same. I want to conclude now. It's 12 p.m. I just argue here why I think that bicoherence is better than PAC. First of all, bicoherence, to calculate it, it's so much faster than PAC. Depends on the implementation, but probably like 600 times faster. Bicoherence is more general. So in general, I've done it here, but general can be calculated between a triple of channel, but in PAC you can do it, the formula like that. And especially you can use PAC can be made robust to artifacts of bicoherence can be made robust to artifacts of volume conduction, but PAC you cannot. And these are the reasons I prefer bicoherence over PAC, because in principle bicoherence is either much better, or at least you see the same thing. Okay, and now I must skip this again. In my summary, I summarize here the main points. That first of all, spontaneous brain activity is nonlinear, but it is not non-stationary. To my opinion, this is a widespread misunderstanding of what stationarity means. Phase amplitude coupling is in general a smeared version of bicoherence, and I prefer bicoherence over classical Bach measures. And finally, but I wouldn't show you experimental result, but we see here new opportunities to study the alpha rhythm. Okay, then I'll stop. I skipped a lot here, but the other parts were too long.
Thank you very much. Thank you really a lot for this very nice talk, and sorry for the time. But we schedule a very tight conference. We recognize it. We are probably the one most tired by the amount of information we collect in these days. But thank you very much. Since Laura agreed with postponing a little bit her talk, we can see if we have a very quick round of questions, if there are any from the audience. I have a very quick question about a more general question about application of Bach, because as far as I know, I'm not very expert, but one thing that is really I have understood as a true application of Bach is to try to unreveal some relationship in higher frequency, because Bach may help you in see what MEG may actually have difficult to see in the higher frequency. Do you have any clue on this? Do you think that Bicoherence can help in this or not?
Yeah, we looked at basically often we see when we say a theta gamma coupling, for example, you see this or also delta gamma. Yes, you can use bicoherence to see that. We've seen this in red data downloaded and in ferret data, which we analyzed ourselves. But whenever people report Bach results in such data, we see the same thing very clearly. We can analyze it very quickly. So, if not exactly sure, but so we do analyze that mostly in invasive with high frequency. I do not see this in EEG or MEG, not at all, really.
Okay.
But I see this in LFP data, ferrets, rats. I see this, but not in EEG, MEG. The only thing I see in EEG, MEG is there might be some experience, but basically you could say the higher harmonics of alpha. That's what I see. But not like theta gamma coupling, I haven't seen. But it could be there, but I'm not saying, well, I just haven't seen it.
Okay, that would be really great in my opinion. I mean, because for example, one thing I don't like about classical Bach measures is that they really looks like some empirical measure. I mean, they show you a recipe to compute them, while Bicoherence, it's really like a compact formula for the matrix. I don't know if you have the same opinion, but this is to me seems another plus to Bicoherence.
Of bicoherence.
Of bicoherence, yes.
I mean, you could. I mean, also Bach measuring are written as a formula, and then there's probably it is when you say, you must filter, and then
it looks like more a recipe here than a formula.
Yeah, that's true. Especially when you just more filter the data, and the filter is always different depending on the low frequency and things like that. That looks more like a recipe. And here, bicoherence is perhaps not so ambiguous. It's like coherence, just with one statistical order, one higher order.
Okay, thank you very much again, a virtual club from Italy, and sorry again for the cut we had to make. I think we can have just now a 5 minutes break, so we can test with Laura if everything works with her audio and video.
And Laura works, I just want to say I must leave here at round 1 or so, or a bit earlier than that, to go to Hamburg. So therefore, I will miss again many parts. But I will hear what Laura has to say.
Okay, thank you.